Harmonics are the foundation of all relations in music. The cosmic microwave background radiation has the same harmonics. Once frequencies for 7 octaves were calculated, we discovered many unique properties of natural tuning. Some of them are going to be reviewed here. The sum of interior angles of a triangle is 180 degrees. Of a square and a circle is 360 degrees. A pentagon is 540. A hexagon is 720. A heptagon is 900. All combined is a major chord. The same chord in equal temperament. Combined numbers of any frequency are always 9.
Link in the description. There are thought to be just 4 fundamental forces or interactions in nature. Gravity, which keeps you on the surface of Earth, the weak force, which is responsible for some kinds of radiation, electromagnetism, which is responsible for all chemistry, and the strong force, which keeps protons and neutrons tightly bound together in the nucleus of atoms. You're probably most familiar with gravity, which at the scale of the Earth, the solar system, and beyond, dominates the universe. But at the quantum scale, the other 3 forces dominate. For example, electromagnetism is a whopping 10 to the 37 times stronger than gravity. It's responsible for keeping the negatively charged electrons near the positively charged protons in atoms. So now you have to ask, since electromagnetism is so strong, then multiple protons in the nucleus of any atom, like helium and beyond, should repel each other very strongly. According to Coulomb's law, the 2 protons in a helium atom experience a repulsive force equal to about 90 newtons or 20 pounds. For something as small as a helium atom, this is a huge force. They should repel each other and fly apart instantly. The reason that these protons don't fly apart is because they are kept glued together by a force that is even stronger than electromagnetism, about 100 times stronger, called the strong nuclear force. It is the strongest force in the universe at the scale of the nucleus. This force is not simply the opposite of electromagnetism, but works through an entirely different mechanism, which, unlike chemistry, is typically not taught at the pre-college level. So most people are not familiar with it.
Of the orbit is the so-called Bohr radius. This image is inaccurate for several reasons. First, the size of the proton is about 50,000 times smaller than Bohr radius. Second, quantum mechanics teaches us that the electron is not confined to a well-defined orbit, nor can it be located accurately. Instead, it occupies a region of space around the proton, called orbital. This simulation depicts the orbitals as clouds of points. The regions with the highest density of points are those where the electron is most probably found. The ground state orbital is called 1s. The 1 is the principal quantum number, which is related to electron energy. The s means that the orbital quantum number L is equal to 0. S orbitals have spherical symmetry, so the probability of finding the electron does not depend on the direction. The radius of the second Bohr orbit is 4 times the Bohr radius. Therefore, we must zoom out. Quantum level 2 comprises 2 values of the orbital quantum number. orbital 2s corresponds to L equals 0. As we see, this orbital occupies a much wider region. Let's make orbital 1s disappear and display only a thin slice of orbital 2s. In this way, we notice a radial node, a distance at which the probability of finding the electron is 0. Again, this is the full 2s orbital. Quantum number L equal 1 gives rise to 3 orbitals called 2p. This is one of them. It consists of 2 lobes which we can consider aligned along the x-axis. The second one, 2py, lies along the y-axis. Finally, this is the 2pz orbital. If we display all 3 orbitals at the same time, the complete electronic cloud becomes somewhat confusing, but shows a high degree of symmetry. The third energy level allows 3 different Ls. Again, 3s orbital corresponds to orbital quantum number 0. It has 2 radial nodes. The outer one is clearly visible in this scene. The inner one is hidden by the surrounding cloud. Just as 2p orbitals, 3p ones have dumbbell shape, but with a radial node splitting each lobe. This is 3px. This is 3py. And 3pz. There are several ways to choose the 5 3D orbitals. This is the most popular one. 3 of them have 4 lobes bisecting the coordinate axis. The fourth one has 4 lobes along x and y axis. Finally, the fifth one has 2 lobes along z axis and a ring-shaped region on the xy plane. As quantum numbers grow, the orbitals become increasingly complex in shape, with new lobes and nodes. For example, this is one of the 7 4f orbitals. This is one another. The average electron nucleus distance also becomes higher and higher. Notice the difference in size with the ground state 1s orbital.
When scientists first measured the motion of groups of galaxies in the 1930s and weighed the amount of matter they contained, they were in for a surprise. They found that there's not enough visible stuff in those groups to hold them together. Later measurements of individual galaxies confirmed this puzzling result. There's simply not enough visible stuff in galaxies to provide enough gravity to hold them together. From what we can see, they ought to fly apart, but they don't. So there must be stuff there that we can't see. We call that stuff dark matter. The best evidence for dark matter today comes from measurements of something called the cosmic microwave background, the afterglow of the Big Bang. But that's another story. All of the evidence we have says that dark matter is there and accounts for much of the stuff in those beautiful spiral galaxies that fill the heavens. So where does that leave us? We've long known that the heavens do not revolve around us, and that we're residents of a fairly ordinary planet orbiting a fairly ordinary star in a spiral arm of a fairly ordinary galaxy. The discovery of dark matter took us one step further away from the centre of things. It told us that the stuff we're made of is only a small fraction of what makes up the universe. But there was more to come. Early this century, scientists studying the outer reaches of the universe confirmed that not only is everything moving apart from everything else, as you'd expect in a universe that began in a hot, dense Big Bang, but that the universe's expansion also seems to be accelerating. What's that about? Either there's some kind of energy pushing this acceleration, just like you provide energy to accelerate a car, or gravity does not behave exactly as we think. Most scientists think it's the former, that there's some kind of energy driving the acceleration, and they've called it dark energy. Today's best measurements allow us to work out just how much of the universe is dark. It looks as if dark energy makes up about 68% of the universe, and dark matter about 27%, leaving just 5% for us and everything else we can actually see. So what's the dark stuff made of?